Hi, welcome to problem 2. This problem is a very short one, but very interesting problem. So basically we have a sum that we're inducting over, and the clue is we might need to use strong induction. We're given this sequence, and now we need to see if it diverges or converges. But let's see what this sequence actually does. So let me enumerate the sequence out. This is 2, this is 3 from the base case of the recurrence relation. These multiply together is 6, 6, 3, 18, 18, 6, 108. Now we can see here that we're multiplying a number on top of a result. And so this looks at least exponential. Because recall an exponential, you have 2 and then 4 times 4, and then times 2, 8, 16. The result you get is multiplied by the same number. So this grows at least as fast as exponential. And now remember from your calculus class or discussion 2b that the sum 1 over n diverges. But what series do converge? Well, you have the sum of 1 over 2 to the k, or you have 1 over, this is a geometric series, because you multiply 1/2 every time, or you have even 1 over n squared. So these converge. And you know that this is exponential, and this is also exponential. So clearly this must converge. So we'll get rid of the diverge option. And now what do we need to prove? So in order to prove that a series converges, the procedure is that you choose a sum that converges and show that every term of the sum of the series is greater than the corresponding term 1 over a to the k. So this is our procedure. Now this will also be what we're trying to prove by induction. So before that, let's just see this in action. So for induction purposes, we want to skip the first term, which is okay because we know that all the other terms added together will be some finite number. So since this is a number, we can skip. So now let's compare this to 1 over 2 to the k minus 1, since we're skipping the first one. Why are we skipping the first one? Well, recall the definition here at the very top. You have 2 parts to it, so it seems logical to not have to worry about the very first part, because we will be building off of it. So 1 over 2 to the k minus 1, this is 1/2, 1/4, 1/8, 1/16. And you can see that these are all greater, which is exactly what we want. So all we need to do now is to formalize this intuition from a rigorous proof by induction. So what are our base cases? Recall that we have strong induction, and then we also have multiple landing spots because we have ak minus 1 and ak minus 2. So we need 2 base cases. So the case where k is 1, right? Then we have 1 over a1 is equal to 1/2, which is less than 1 over 2 to the 1 minus 1, which is equal to 1 over 2 to the 0, which is 1. So 1/2 is less than 1, check. K equals 2, 1 over a2 is 1/3, which is less than 1 over 2, check. So we need these 2 base cases so then we can use k minus 1 and k minus 2 together. Now, inductive hypothesis assume that our inequality 1 over 8k is less than 1 over 2 to the k minus 1 for all 1 less than k less than n. Alright, so now that we've assumed that, our inductive step will then be, we want to prove a to the k plus 1 is less than 2 to the k. So prove this. A to the k plus 1 is by definition what you see at the very top, 1 over a to the k plus times k minus 1. And using the inductive hypothesis, yes, we can create a bound on this of 1 over 2 to the k minus 1 times 2 to the k minus 2. And the reason is that we know that these two together will be smaller than these two from the inductive hypothesis. And so let's keep going. This simplifies to 2 to the 2k minus 3, which is less than 1 over 2 to the k for all k greater than 3, or equal to 3y. So let's look at situations where 2 to the k minus 3 is greater than k. This means that k is greater than 3, basically. So, or you can add equal to, it doesn't really matter. So yeah, that shows that our inductive step is true. So we proved our inductive step. We proved base cases. And these two together with the inductive hypothesis all come to prove that every term of the series is greater than. So every term is greater. And we've completed the problem pretty much. The sum does converge. Now I'll show you an alternate solution. You can skip to the next problem, or you can listen to my alternative solution, and I'll be back right after this. Hi, welcome to the alternate solution for problem 2. Last time we looked at 1 over 2 to the k minus 1. Now why don't we try looking at 1 over the sum of 1 over n squared. So does this converge? Well, we can see that 1 over n squared is less than 1 over n times n minus 1, since this is smaller, equal to bigger fraction. Denom is bigger fraction. Now this is equal to, by partial fraction decomposition. Now we need to figure out how to break this to a over n plus b over n minus 1. And to do that, we multiply all the sides. And then we can see that an plus bn minus a equals to 1. This has to be 0, and this has to be 1. So negative a equals 1, a equals negative 1, and b is equal to 1. So 1 over n times n minus 1 is equal to negative 1 over n plus 1 over n minus 1. Now, how does this series look like if we sum it? Let's start at n equals 2 because we have n minus 1 here. So negative 1/2 plus 1 minus 1/3 plus 1/2. Right? This is the n equals 3. This is n equals 2. Minus 1/4 plus 1/3, and so forth. And you can see that apart from 1, 1/2 cancels out, 1/3 cancels out, and 1/4 presumably cancels out as well. So we can see that this sum does converge to 1, and so 1 over n squared converges. So now all we need to do is prove that 1 over ak is less than some sort of 1 over k squared. But as soon as we test these examples, remember these, if you do a1, 1/2 is less than 1, that's true, but 1/3 is not less than 1/4. So we'll have to change this a little bit. And as you can see, if we try 1 over ak is less than 1 over k minus 1 squared, this might all work out. Because instead of these old base cases, we need to start at a2 because we have k minus 1 involved. And then we have a to the k minus 2. So if we start at a2, 1/3 is less than 2 minus 1, 1. That's good. 1/6 is less than 1/4. That's good. And 1/18 is less than 1/9. So basically, we only need these two base cases, but this last one's for illustration. These numbers are indeed smaller. So using this, let's prove by induction that all these terms are less than their corresponding squared terms. So remember that 1 over ak is less than 1 over k minus 1 squared is what we're trying to prove. Our base cases are a2 and a3. So inductive hypothesis, assume that this is true for all, remember we start at 2 less than n. Let's actually assume 3 because we have the a to the k minus 2. So now inductive step, a to the k plus 1 is 1 over a to the k plus 1, remember, is, we want to prove that this is less than 1 over k squared. So 1 over a to the k plus 1 is equal to 1 over ak minus 1. And by the inductive hypothesis, this is the same process we went through last time. This is k minus 1 squared. This is k minus 2 squared. And the squares can come together. And if we FOIL this out, we have k squared minus 3k plus 2 squared. And we claim that this is less than 1 over k squared for all k greater than or equal to 4. Now we left off with the inequality 1 over k squared minus 3k plus 2 squared is less, we claim this, k squared. How are we able to claim this for all k greater than or equal to? If we look at this expression here and plug in 4, we get a 16 minus 12 plus 2 squared, which is 4 plus 2 squared, which is equal to 1 over 36. This is all 1 over. And this is less than 1 over 16. If we tried k equals 3, then we get 9 minus 9 plus 2 squared, which is not less than 1 over 9. So this is for all k greater than or equal to 4. And so this actually ends up proving our inductive step. And so we have therefore proved that all terms in 1 over k minus 1 squared is greater than the corresponding terms in 1 over a to the k, and so the series converges. Great, let's move on to problem 3.